Hello everyone. Let's continue our discussion on classification. Specifically, we want to discuss multi-class classification. We have already studied MNIST dataset. Specifically, we trained a binary classifier, use SGD classifier on MNIST dataset. For that specific example, we use whether it's 5 or not, and try to train the binary classifier. We spend a lot of time to discuss performance measures. You should know the importance of confusion matrix, the importance of the definition of all those metrics such as true positive rate, specificity, precision, recall, and as a result, you should know what is ROC curve and what is area under curve, AUC. Now let's focus on a little bit different, as would be multi-class classification. We discuss error analysis. We also give you some examples of multi-label classification as well as multi-output classification. What is multi-class classification? Multi-class classifier can distinguish between more than two classes. So it's not only just two classes. Now we're talking about a full-fledged multi-class classification. In the MNIST example, you have digits from 0 all the way through to 9. So you have 10 different classes. You could leverage logistic regression, random forest, or naive Bayes for a multi-class classifier. We're going to study linear regression and logistic regression in next section, and we're also going to study what is random forest in a couple of week time frame. And for binary classifiers, you could leverage two major methodologies. One is SGD classifier, which we already used in the binary classification case, or you could leverage support vector machine classifier, which is something that we're going to study shortly after regression methods. For multi-class classification, there are two types of strategies. One of them is called one versus rest strategy. The way that you do it, you get multiple binary classifiers and then output the highest score based on each binary classifier. So in the MNIST example, you can start with 0, non-zero, 1, non-1, 2, no, not twos, things in that nature. So it's a one versus the rest strategy, but it's not each individual it's not each individual ones, but we are hoping that we are open to open to the case that one versus the rest. One or not ones, but not ones included multiple not ones, like 0, 2, 3, 4, 5, etc. And the other strategy is called one versus one strategy. So, for example, use one strategy, classifier to distinguish 0 and 1s, and then 0 and 2s, 0 and 3s, so on and so forth. So as you can imagine, it would be n times n minus 1 divided by 2 classifiers. That's called one versus one strategy. Support vector machines or support vector classifiers, as we see, is not scalable with the size of the training set. That's why usually we don't want to use 1 versus R strategy for SVC, usually use OVO, 1 versus 1 strategy. However, most other classifiers are using 1 versus a rest strategy. Good news is scikit-learn helps you to pick the proper strategy. It's either 1 versus OVO or OVR, so you don't really need to worry about it too much. Let's look at an example on SVC. So far, we actually didn't specifically tell you what is support vector classifier yet, which is something that we're going to discuss in further detail in the coming weeks. But at least you could get a preliminary understanding of it. So you could have this SVC class, and then you define this SVM underscore CLF classifier, SVM classifier, and then you use a fit function to train your X train data versus Y train, and then you try to predict use your SVM CLF classifier. And then you could come back with that decision function. As once you train that, you use SVM underscore CLF dot decision function to access the score. They actually come back. And then you can see that this essentially is aligned from the original data set. The score for this particular digit, some digit is the first image, remember X0, right? And then it is 0 if it's 0, then it has corresponding value of 2.9. Predicted to be 1 has corresponding of 7, and all the way you can see that it's 5. 0, 1, 2, 3, 4, 5 indeed have the highest score. So trying to output this score, which is argmax of this sum digit score, turns out to be 5. As a result, the class of this particular image, sum digit X0, is indeed 5. Again, scikit-learn detects when you try to use a binary classification algorithm for multiple class classification task, and it automatically runs OVR or OVO strategy depending on the algorithm. So here, give you the example of using SVC to do multi-class classification. Let's look at the error. Once you have a model, multi-class classification model, let's look at the error. You leverage cross-validation again and come back with a confusion matrix. Confusion matrix is no longer as simple as what we saw 2 by 2, right? In this case, is 10 by 10. It's actually 9 by 9. Let me see, 0, 1, 2, 3. It's 1 by 9 by 9. Let's go back. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9. Also, yeah, it's really 10 by 10, right? So it's because 0 to 9, so that you have 10 dimensions, and in terms of the number of rows, it would be 10, and number of columns should be 10 as well. So it's a 10 by 10 matrix. Instead of that 2 by 2 matrix that we had in a binary classifier, remember it's 5 or not 5. In this case, it is 0, 1, 2, 3, 4, all the way to 9. And then on this row, essentially that's actual, and on the columns would be your predicted value. So what do you see here? For the diagonals, it has a fairly large number. Essentially says a lot of the zeros is correctly to be predicted to be 0. A lot of ones is correctly predicted to be ones, so on and so forth. That's good news, right? So you would want to look at this. Of course, some of the actual being zeros turns out to be 22 of them predict to be 2s, right? And then some of them, 222 of them, of the zeros are predicted to be 8. This is one way to look at your error analysis of multi-class classification. We could also plot that matrix. Just because of the diagonals are so big, and then in this matrix, you can see in this plot, you can see that we really don't see a lot of information. Let's further to do a little bit different. That is, instead of using the original number, which is really big, some of them are big, especially for the diagonals, and some of them are small for the off diagonals. What you can do is you do the normalization. You use confusion matrix divided by the row sums so that you normalize them. And as a result, you can see that once you plot that, turns out to be more striking in terms of the visualization. What you saw here is a lot of the images somehow are misclassified as 8. And once you know this, you probably want to dig into a little bit more to enhance your algorithm to see if my algorithm can do better on the 8th. If I would be able to do that, essentially I would figure out a way to enhance my algorithm. So that this is the reason that you want to learn this. This is helpful for you to enhance the algorithm. As an extension of the multi-class classification, we want to discuss something called multi-label classification. So what is multi-label? If you think about what we just had, 0, 1, 2, 3, 4, all the way to 9, you only have one label. It's either 0 or 1 or 2 or 3, so on and so forth. But in this case, we define something new. We have multiple labels. For example, we could see that based on the y-train's value, to see if anything that's larger than equal to 7, we call it y-train large, or anything that is with the remainder divided by 2, mod by 2, and with the remainder of 1, we define them as odd. And then for the ones that you have those two labels, either large or odd, or large and even not odd, or not large but odd, not large and not odd. So you have a new label that is a multi-label that incorporates both of the y-train underscore large and y underscore train underscore odd. And you leverage something called k-nearest neighbor classifier to train your model that have multiple label. You're able to predict some digits that, again, this some digit is the first image in your data set, which is x0. You could test on some others as well, but here we just use x0 as an example. x0 is 5, as you know. It is not large, but it is an odd number, right? That would be something you could leverage. That's called multi-label classification. Last but not least, that's multi-output output classification. So the whole idea is not only give you one output, you can have multi output. To illustrate this, let's build a system that removes noise from images. It will take as input a noisy digit image, and it will hopefully output a clean digit image, represented as an array of pixel intensities, just like the MNIST images. Pixel intensities, which is 28 by 28 matrices, remember? Notice that the classifier's output is multi-label, one label per pixel. And each label can have multiple values. Pixel intensity ranges from 0 to 255. It is thus an example of a multi-output classification system. So you can see here in terms of coding, what you're trying to do here is you have random noise that you initialized, which is 784 columns, and X-string 60,000 of that rows, and you random initialization, a random number between 0 and 100, and that noise, you add that noise to your X-string. You also add that noise to your X-test. Then you call this as X-string modified and X-test modified. And Y-string modified versus Y-test modified are actually the original X-string and X-test. And then you this is your noisy image. This is really what without any noise. And then you do, what you did was train the classifier and make it clean this image. Then the output of doing that is trying to clean this image output with something more like this at the bottom of the chart. And you can see that it has some merit about this algorithm because it comes back with something looks a little bit fuzzy, but at least you're still able to differentiate this digit. You know it is 4. It is a 4, just not as clear as it was. It's fuzzy, but we are able to differentiate it to be the number 4. This is another extension of multi-class classification. It's called multi-output classification. Okay, this actually concludes our discussion on multi-class classification. And in your study, you should pay attention to the error analysis, try to digest the output of what you got from the algorithm. I'll stop here. Thank you.